let's review some temperature conversions. Now you're not going to have to memorize these formulas. You will have a sheet with formulas, or you'll have formulas on the test, so you do not have to memorize these. Y'all, do not make this hard. Do not spend much time studying on it. All you got to do is plug in numbers. Okay, you all are very, very capable of plugging in numbers. So the Celsius scale is based on the melting point, or the freezing point of water, which is 0 degrees Celsius, and the boiling point of 100 degrees Celsius. Your Kelvin is based on absolute zero, when there is absolutely no molecular motion occurring. That's saying that all the molecules have stopped vibrating, have stopped moving. Fahrenheit, I don't have a clue. You have to Google what that junk's based on. I don't even know. And I'm 50-something years old, 51 or 52 years old. I still have no idea what that's based on. So you can figure that out if you want, but I wouldn't spend the time on it. So let's just do some conversions here. Remember, we just plug in the numbers. So let's say we want to convert 98.6 degrees Fahrenheit to Celsius. This happens to be our body temperature, normal body temperature for normal people. Not me, I run cold. But so we say we're going to use this one. We're going, we want degrees Celsius. We have degrees Fahrenheit. Okay, so we're going to say degrees Celsius equals the Fahrenheit, which is 98.6, minus 32 times 5/9. So remember, you do that PMDA, I don't know, please call my dear Aunt Sally, remember, I don't know. You do that parentheses first, don't forget. However that goes. Okay, so 98.6 minus 32, 66.6 times 5, and then we're going to divide whatever we get by 9. Okay, so times 5 equals 333. We're going to divide it by 9, 37 degrees Celsius. Okay, so the normal body temperature for a human in Celsius is 37 degrees. Fahrenheit is 98.6. Next, let's convert 100 degrees Celsius to Fahrenheit. Okay, so let's see what the boiling point of water is in Fahrenheit. So now we're going from Celsius to Fahrenheit, so we say degrees Fahrenheit equals, okay, so we say degrees Fahrenheit equals degrees Celsius times 9/5, so that's 100 degrees times 9/5, close our parentheses here, plus 32. Okay, so 100 times 9 is going to give me 900. Remember, you do them parentheses first. So you say 100 times 9, that gives me 900. Whoops. Divide it by 5. And we're going to add 32. So 212 degrees Fahrenheit is what water boils at in the degrees Fahrenheit. Okay, now let's go from Celsius to Kelvin. So when you're going from Celsius to Kelvin, you just say the degree, the number in Kelvin minus 273. Okay, so hold on. We're going Celsius to Kelvin. So we're going to say the number in Celsius, degrees, plus 273. Kelvin equals whatever we have in Celsius plus 273. Okay, so Kelvin equals whatever degrees Celsius plus 273. Now you may see the number 273.15 used here, but that 0.15 is, as long as we're adding 273, we're going to be fine. So we're going to say 35 plus 273, 35 plus 273, that's 308 degrees Kelvin, or 308 Kelvin. They don't say degrees. We just say K, 308 K. Now when we're going from Kelvin to Celsius, we subtract the 273. Okay, so notice here we're going from Kelvin to Celsius. So we say whatever we have Kelvin minus 273. So we have whatever Kelvin minus 273. So we got 372 minus 273, 372 minus 273. That's 99 degrees Celsius. While we are dealing with temperatures and such, let's just take a real quick look at solids, liquids, and gases. And let's just take and then remember you got plasma also. Okay, so remember, if we're to make real quick little diagrams, solid are a definite shape, a definite volume. They're going to, in comparison, have the lowest amount of movement and the lowest amount of energy. And you're not going to really be able to compress a solid. Okay, compress means to push it and make it tighter. Okay, so they're not going to be, they're going to have a very low compressibility. Okay, so the compressibility is going to be kind of low because they're already, those molecules are already packed in there. Now, a liquid, okay, remember liquids, they take the shape of their container. So we say that they have an indefinite shape. And all this is from your physical science class. I think pretty much all this right here is just review, but I want to review it with you. They have an indefinite shape, but they have a definite volume. Okay, so water, for example, when it's in its liquid state, the volume is definite. You could have 5 milliliters, you could have 10 milliliters. They have sort of a medium in comparison movement. The energy in comparison is medium. Now, liquids can be compressed somewhat. Okay, they're kind of hard to compress because a liquid is only going to go so far, but yet you can, to some degree, have a little compressibility. Okay, meaning that you can take that liquid and you can put pressure on it and those molecules will pack a little bit tighter. Let's take a look at gases. Gases are all spread out. They're going to go wherever they can go. So we say that they have an indefinite shape. They have an indefinite volume. They have a high amount of movement, and they have a high amount of energy. And these have very high compressibilities. meaning that you could take a gas, and just like whenever you take a some kind of a spray can that turns instantly to gas, like those air cans where you clean your keyboards, well, that gas is compressed in there. And so you can put, you know, in order to compress a gas, you just add a lot of pressure. Just like in your tires. You fill your tires up, you keep on filling them, you keep on putting more air in there, and that air compresses. So gases have a very high compressibility. Plasma, the thing we really just need to know, you know, remember plasma is a charged gas, and we really, in this class, don't deal with plasma that much. Okay? So, if you want to know what to really concentrate on, I would not spend a lot of time on plasmas, but I would just remember, you know, that your gases, they have high compressibilities, high amounts of energy, high amounts of movement. Their shape and volume are indefinite. They go wherever.